All right, guys, let's start. So now we are doing your chapter number 3, lesson number 3, chapter 1, fundamental probability. See, this particular lesson, right, expectation and variance, is basically the language of quant finance, right? Before we start the slide, understand one thing, that almost the entire field of quant finance is built on answering two questions. Question number 1 is about what return do I expect to earn? This is answered by your expected value of X, expected value or mean. Question number 2 is how uncertain is that return? That is answered by your variance of X. Everything from your portfolio management, your capital asset pricing model, the Black-Scholes, Monte Carlo simulations, war, credit risk model, machine learning in finance, eventually come back to these two concepts, right? So let's dig deeper, try to understand more. Now, first part here, right? So when you talk about your uh, introduction to expectation and variance, probability and statistics, chapter 1, fundamental of your uh, probability, lesson 3, uh, expectation and variance, right? The lesson is one of the most important lessons of quant finance because expectation is equal to reward, variance is equal to risk. The entire investment industry is basically trying to maximize the first and minimize the second, right? So when we talk about expectation and variance, four measures of uncertainty, the slide says expectations and variance are two fundamental concepts used to describe a random variable. Let's try to understand this deeply. What is a random variable? A random variable is simply a number whose future value is uncertain. For example, variable tomorrow stock return, right? Possible values -10, +5, +20, future interest rate 3%, 4%, 5%, option payoff, various values, credit loss, unknown. Since future outcomes are kind of uncertain, we need a way to summarize them. That's where expectation and variance comes in, right? Expectation answers on average, what should I expect mathematically? Value of X. Variance answers how much uncertainty exists around that average, mathematically variance of X. From the quant finance perspective, suppose two stocks, stock A and B, expected return 10%, 10%, but both have identical expected return. But stock A has volatility 5%, stock B has volatility 40%. Stock B is much riskier, right? Therefore, expectation alone is not enough. You need variance. This is exactly the foundation of your modern portfolio theory, right? So very basic, very simple stuff till now. No formula, no maths, very simple, very okay. Then we get into intuition, mean as reward, variance as risk. Again, a lot of theory. The slide contains one of the most important ideas in finance. Expectation mean measures the average outcome or long-term average. If you repeat an experiment infinitely many times, average outcome is equal to expected value. This is called the law of large number. Variance measures spread around mean. A large spread means greater uncertainty. A smaller spread means more predictability. Example, investment A returns 9, 10, 11%. Average 10, very stable. Investment B returns are -30, 10, and 50. Average 10, same expectation, huge variability, much scale. Okay. Portfolio management insight here is this leads directly to reward to risk trade-off, which later becomes your Sharpe ratio, expected return minus risk-free rate divided by sigma, one of the most important ratios in finance. Okay. Again, a lot of theory. I'm not spending a lot of time here. Uh, this is pretty basic stuff, guys. Right? We'll spend time where we are actually getting into the quant or maths part. Next one is expectation, weighted average of outcomes. The slide says expectation is the weighted average of all possible outcomes. This is the key idea. Not all outcomes matter equally. More probable outcomes receive larger weights. General formula for a discrete random variable, we see, right, expected value, right, is equal to summation I xi p is equal to xi, right, where xi is the outcome, px is equal to xi is the probability. For example, suppose outcome is 100, probability 0.7, 200, probability 0.3. The expected value of X will be what? 100 into 0.7, that's 200 into 0.3, 70 plus 60, 130. Expected value is 130, right? Financial interpretation is expected return when you take, right? So if you take expected return, right, it is nothing but summation RIPI, right? So expected payoff, that's what we are getting. Expected value of payoff, expected loss, expected value of loss, expected exposure, expected value of exposure. These concepts appear everywhere, right? All theoretical till now, nothing special. Let's go ahead, guys. Now, once we have seen this, we get into the next part. From here, we start with a little bit of maths. Discrete random variable expectation formula. Now, the slide gives the formula, a formal formula, which is this, which I told you. Example, let's say fair die, possible outcomes 1, 2, 3, 4, 5, 6. Probability of x is equal to 1 by 6. Substituting, when we put the values, we get this 3.5. Important insight, 3.5 is not an actual outcome, right? You can never rule a 3.5. Yet, expected value of x is 3.5. This is one of the most first conceptual hurdles students face. Expected value is longer than average, not most likely outcome. Very important distinction you need to know. Finance connection here is an option may have expected value of A of, let's say, 12.35. Even though the actual payoff might be 0, 10, 25, 30, 50, whatever. Right? Expectation doesn't need to be a possible outcome. Keep that in mind very, very clearly. Okay. With that, we go to next part, which is continuous random variable expectation formula. Again, in real finance, stock prices, interest rate, FX rate, commodity prices are usually modeled as continuous variable instead of probabilities. We use a probability density function PDF, and we have this formula which we have. So think of integration as summing infinitely many tiny varied outcomes. Normal distribution is given, right? The x n mu sigma square. Then expected value of x is mu. Interpretation mu is the center of distribution. Everything balances around it. Why quants care about it? Because many models assume that returns also are like x, right? Follow a normal distribution mu sigma square. Mu is expected return, sigma is the volatility, sigma square is the variance. This appears in CAPM, portfolio theory, VAR, model, right? Which we need to understand. Fine. Then we get into the next part, which is your expectation summary, discrete versus continuous. This is summary. The slide compares the two formulas, right? Which is given. Discrete case, formula is given. Continuous case, formula is given. You compare both of them. Core ideas, both formulas are actually identical. The only difference is discrete is weighted sum, continuous is weighted integral. Conceptually, they are the same thing. In quant perspective, please understand Monte Carlo simulation converts continuous problem into discrete approximation. Instead of having your what you say integral of your x fx dx, right? We estimate expected value of x, right? Almost like equal to 1 by n. Okay, these are the most important areas in modern derivative pricing. Fine. Then we get into next part. Slide number 8, expectation versus expected return, right? Again, now we move from probability into finance. Asset return R, possible returns R1, R2, R3, probability P1, P2, P3. Expected return, if we take, is equal to sigma RIPI, portfolio return, portfolio weights are W1, W2, Wn, then ERP is equal to sigma WI value of RI. Extremely important result. Expectation is linear, right? We have seen in the previous chapter, right? Expected value of your AX plus BY. Okay. This simple property makes portfolio mathematics possible. Without linearity, modern portfolio theory would become much more difficult, right? Variance of a random variable. Okay. Now we reach the second pillar, definition variance of x is equal to expected value of x minus ex square. Let's understand every p. Step 1 is calculate the mean. Step 2 is deviation from mean, x minus expected value of x. Step 3, square the deviation, x minus expected value of x, the whole thing, whole square. Squaring presents or prevents your positive and negative deviation from cancelling. Step 4 is take the expectations, expected value of x, e minus x square. Right, this gives the average square deviation. Why variance matter? Because large risk, large variance, small risk, small variance. Finance interpretation is quantitative finance. Sigma is under root of variance x. Standard deviation volatility is often more important than variance itself. Black-Scholes, war, Gauge, portfolio theory, all these volatility we need to understand, right? Okay. Then we get to next slide. Variance shortcut formula. The formula used constantly. Variance of x is equal to expected x square minus ex expected value of x whole square. You can expand it, right? You this can be calculated very easily, right? So it can also be written like this. Uh, it's not difficult, right? So if you have, let's say, variance of x, what is variance of x? Expected value of your x minus expected value of x square, right? You expand that. If you expand that x minus ex square, right? Ultimately, what are we getting, right? You are expanding that, right? Ultimately, is x square minus 2x, expected value of x, expected value of x square, right? So this whole thing, right, has the expected value, right? And taking expectation, right, variance of x reverts into e x square minus e x square, right? So we get this formula, right? Uh, Final formula is this. Why Quants love it? Because much faster computationally, instead of calculating every deviation from the mean, compute expected value of x and expected value of your x square, then apply variance of x is equal to expected value of x square minus expected value of x whole square. Where this appears? Portfolio variance, covariance matrices, factor model, risk engines, Monte Carlo simulation, machine learning, loss function, volatility forecasting, right? So again, this is loved by quants because this is much faster. Right? You don't have to follow that, okay, four-step procedure which we saw in the earlier this formula, right? First, find the ex, then do x minus ex, then do x minus because see, if you see the first one, right? In the first one, you have to do your first you find if you first you need to find first you need to find your ex, then you have to do x minus ex, then you have to do square of that x minus ex square, then you need to find the expected value. So it's a four-step procedure, right? So this one is a one-step procedure, right? This is one step to find variance. This is four step. Okay. This is four steps. You want the one step, right? But quants love it because much faster computationally instead of calculating every deviation from the mean. Go to ex and ex square, then apply variance of x, ex square minus ex whole square, where this appears portfolio variance, covariance matrices, factor model, risk engine, Monte Carlo simulation, machine learning, loss function, volatility forecasting, right? Overall, till now we have done 10 kind of slides, right? Everything we have studied so far boils down to reward, expected value of x, expected return, risk, variance of x, or sigma under root variance of x. Volatility, this eventually evolves into the entire framework of modern finance. Optimal portfolio is equal to max expected return divided by risk, which is the foundation of Markowitz portfolio theory, CAPM, FGN frontier, Sharpe ratio, Black-Scholes, risk neutral pricing, quantitative risk management. These first slides, right? First few slides are not just introductory statistics. These are the mathematical foundation of which almost every quant model is built. Okay. Then we get into the next part. Now we are looking for variance for discrete random variables with example. Okay. So we need to understand that very, very clearly. Okay. So when you talk about discrete random variable x with PMF, right? Variance of x is given. Right now, this particular, if you look at this particular slide, right? So what is happening here is that we are uh, taking a fair six-sided die, right? We are taking an example, right? We're trying to understand with an example that there's a fair-sided die where sample space is 1, 2, 3, 4, 5, 6, probability of x is equal to x equal to 1 by 6. Expected value, you've already calculated in the previous example, right? So that gives us your, what do you say, expected value of x equals 3.5, right? So that is what we have it, and then we have variance of x is equal to x minus 3.5 square, right, into 1 by 6, right? So compute the standard deviations, sum it up, right? You get it. That the variance of a fair die roll is 2.92, right? This is just a solution to one of the questions we need to keep in mind, right? So, whenever you are trying to solve your numerical, right? Please keep this in mind because uh, you should know how to solve, right? Variance for a discrete random variable. Okay, keep that in mind. Fine. So this is good. This is very very good. Yeah. So for a discrete random variable, this is a formula, right? Xi minus ex square probability of x equal to xi used. You know the value x minus expected value of x for 3.5 square 1 by 6. So 1 minus 3.5 square 6.25, 2 minus 3.5 square 2.25, 3.25, then 0.25. Yeah. And you add it, right? And you got it, right? So it's very straightforward, right? Okay. Okay. Next one is for same thing, right? We're doing the same thing now, variance for continuous random variable. And when we do variance for continuous random variable, obviously we have to follow the integral. Right here, the integral is minus infinity to infinity x minus ex square, and there we had probability x equal to x. Here we have the fxx, right? Fxx we have, right? And using the shortcut formula, I told you, right, that this formula used a lot. Why? Because this is one step formula, right? So you got the ex square. Ex square now, I have to find out that is your minus infinity to infinity minus x square, what you say, uh, fx x dx, right? So that's what we get, right? So this is also given, right? And finance relevance, continuous time returns, and price model require integrals. Variance becomes the base volatility input for many risk model. Key takeaway: continuous variance is computed by integrating square deviations. Integrating square deviations from the mean across all outcomes, right? So we are now using an integral approach, right, to calculate the same thing as we did in the previous question, right, or previous slide, right? So one is variance for discrete random variable, one is variance for your continuous random variable, right? So both have similarities, but you need to understand that both are trying to achieve a different outcome, right? So that's what we are trying to do, right? So remember that very very clearly when you are trying to solve this, right? So that's the whole idea. Okay. So one is your again, sorry. One is your variance for discrete, right? Random variable, discrete random variable. With example, we move from the definition of variance to actually calculating it. We know the definition variance of x equal to expected value x minus expected value of x square. The formula says take every possible outcome, measure a distance from the mean, square that distance, and then average everything by 2 square. Suppose the mean is 3.5. Values below 1 minus 3.5 minus 3.5. Values below above mean 6 minus 3.5 is 2.5. You simply average the deviation minus 2.5 plus 2.5, it becomes 0, right? This disappears. It's obviously wrong. Therefore, we square it. Minus 2.5 square equals 6.25. Now, every deviation contributes positively, right? And then we take a fair die, possible outcomes 1, 2, 3, 4, 5, 6, mean expected value is 3.5, probability of x equal to x, 1 by 6. And then we calculate the square deviations, right? 1 minus 3.5 square, 6.25, 2 minus 3.5 square, 2.25, 3 minus 3.5 square, 0.25, 4 minus 3.5 square, 0.25, 5 minus 3.5 square, 2.25, 6 minus 3.5 square, 6.25. Notice something very beautiful here. The deviation is symmetrical around the mean. The symmetry is why the normal distribution becomes mathematically convenient later. You compute the variance, you added all the deviations, 6.25 plus 2.25, 0.25, 0.25 minus plus 2.25, 6.25 divided by 6, 2.9167. The quant finance interpretation here is suppose two assets have identical expected return. Asset A in return 10, variance 2, asset B in return 10%, variance 50. Most investors choose asset A. Why? Because variance measures uncertainty around expected return. This is the beginning of risk-adjusted investing. Okay, same logic I put in your variance for continuous random variable. Again, previously discrete case use summation, now continuous variable use integration. The formula is in front of you. Variance of x equal to integral minus infinity to infinity x minus x square x equal to x the whole square fxx dx. Fxx is the probability density function. Interpretation, think of integration as summing infinitely many tiny probabilities instead of using your uh, summation. We are using your integral because there are infinite many possible outcomes. Shortcut formula is also given, which is this, right? Where ex square is this, right? Why Quants love this formula? Because imagine calculating volatility for billion of stock return, thousand of option paths, large Monte Carlo simulation, nobody computes x minus ex square. For every scenario, instead risk engines calculate ex square and ex whole square separately, then subtract. This gives enormous completion time. Connection to Black-Scholes assume DST. If I try to find out, right? DST is equal to mu ST dt plus your sigma ST EWT. The volatility parameter sigma comes directly from variance. This variance becomes one of the most important inputs in derivative pricing. We should know, right? So then we go to standard deviation. Standard deviation, the practical volatility measure. Again, this is an extremely important slide. In real life, people really talk about variance. They talk about standard deviation. Sigma x is equal to under root of variance x. What is square root? Variance as squared unit. Example, if return is measured in percentage, then var r variance of return is measured in percentage square, which is hard to interpret. Taking square root gives sigma equal to under root of variance of r. Now units becomes percentage. Again, much easier to understand. You have die example. Variance is 2.9167. Standard deviation under root of 29167 1.7078. Financial meaning is this is where the word volatility comes from. Volatility is simply sigma, right? Example, stock A sigma 10%, stock B sigma 40%, stock B sigma 4, therefore it is riskier. Interview insight, if you go for quant finance interview, if someone says the annual volatility of Tesla is 60%, it literally means sigma is equal to 60%, right? Which is standard deviation of annual return. Why standard deviation dominates finance? The huge in Sharpe ratio, war, Black-Scholes, capital, volatility, risk management, right? Everywhere. Okay. So remember that point. Then we go to the next slide, right? We go to slide number 14, linearity of expectation. This is property we have studied already. The property is one of the greatest gives mathematics, gives finance. Expected value of your ax plus b by a expected value of x plus b expected value of y. This means expectation distributes across addition. Suppose ex is equal to 10, ey is equal to 20, then ex plus y is equal to 30. No extra work required. Scaling ecx is equal to c into ex. If ex is equal to 5, e10x is equal to 50. Why this is important? Simple idea. Because portfolios are some of assets without linearity, portfolio mathematics would become impossible. Expectation is linear even if variables are dependent. No independent assumptions required. This is very common question, right? Uh, in interviews and other places, for expectation, ex plus y is equal to ex plus ey. Always no independence needed. Okay. So that's very, very important thing, right? No independence assumption needed here. It always, right? Then portfolio expected return using linearity. Now we apply the previous slide to finance. Portfolio return is equal to RP is equal to W1 R1 W2 R3 and then W1 RN. Applying linearity, we get W1 expected value R1 W2 expected value R2 W1 expected value RN. And then we use the matrix form. This becomes ERP is equal to matrix W is equal to, you can put it, your W becomes your matrix form. W1 W2 Wn, and mu also is expected return of 1, expected return of 2. The quant interpretation, the formula powers portfolio optimization, hedge fund, robot advisors, risk systems, every institutional portfolio use this. Important insight is notice to compute expected return, ERP, right? We don't need covariance, we don't need correlation, we don't need independence, only expected return and rate. So portfolio expected return is a weighted average of expected return. Independence is not required to compute ERP. Key takeaway, expected return is simple to combine because expectation adds linearly. Okay, that is what we have. Then we get into your slide number 16, variance of a sum of random variables. Now we reach one of the most important formulas in portfolio theory. Unlike expectation, variance is not linear. Variance of x plus y is equal to variance x plus variance y is equal to 2 covariance x y. Right? Covariance of x y is given E X minus EX and Y minus EY. The expected value means covariance measures two assets move together. If they move together, covariance X, Y greater than zero, risk increases. If the opposite, covariance X, Y less than zero, risk decreases. This is your diversification, right? This is what is diversification. Single variance sum is the reason diversification works. Without covariance, portfolio theory would not exist. Suppose, let's say, airline stocks lose money when oil rises, oil companies gain money when oil rises. Holding both creates covariance less than zero, which reduces risk. Deep inside is most beginner things. Portfolio risk is average asset risk. Wrong. Portfolio risk depends highly on covariance. This Markowitz Nobel Prize winning insight, right, which we need to understand. Okay. Then we go into your slide number 17. Again, independent case, variance kind of add. Special case, a variance, kind of independent, then covariance of xy equals zero. The variance formula becomes variance of xy, right? Of variance x plus y. If x and y are kind of independent interpretation, no interaction, no diversification effect, no correlation effect. Important real world observation, financial assets are really independent. In fact, during crisis, correlation tends to one, correlation spike, assets start moving together. Diversification suddenly become less effective. This happened during your 2008 financial crisis, COVID crash, LTCM collapse. Let's say you are going to quant finance interview. Does zero covariance imply independence? Answer is no. Independence implies zero covariance, right? But zero covariance does not necessarily imply independence. Very common interview question, right? It's not vice versa, right? So remember that. Okay. Zero covariance does not necessarily imply independence. Independence means zero covariance. Zero covariance. Zero covariance does not mean independence. Then we get into the next one. Portfolio thrilling, total risk of a two asset portfolio. Very simple. Now we combine everything. RP is equal to W1, R1, W2, R2. Variance RP is equal to W1 square, variance R1, W2 square, variance R2 plus 2 W1, W2, covariance R1, R2 using covariance R1, R2, correlation sigma 1, sigma 2. Variance of RP is given, right? This is one of the most famous equation in finance. Special case, perfect positive correlation, correlation equal to 1. No diversification, zero correlation, moderate diversification, perfect negative correlations, potentially eliminate risk completely. This is the mathematical basis of hedging, which we need to remember, right? Then we get into the next one, asset return, mean as return, variance risk. Very simple, guys. This slide summarizes finance expected return, ER equal to reward, risk, variance R, or sigma R, under root of variance R. Investors always face risk, reward risk. Example, investment A, let's say we have return 15%, sigma 30%, investment B return 10%, sigma 5%, which is better. There's no universal answer, right? Depends on investor risk appetite. This leads directly to utility theory and portfolio maximization. Very simple, very straightforward. Then we go to portfolio theory, Markowitz mean variance framework. Harry Markowitz introduced the mean variance framework. This is where modern finance truly begins. Harry Markowitz asked, how should investor choose portfolio? His answer, use only two inputs, reward, ERP, right? Portfolio expected return, variance of RP, right? Where this symbol, right, which looks like sigma, nothing but a covariance matrix, right? Optimization problem, either maximize return for given risk or minimize risk for target return. This generates your efficient frontier, your capitalist pricing model, your Sharpe ratio, modern asset allocation. The most important formula here is variance is given by this. Please understand the single equation used by Black-Scholes, BlackRock, Goldman Sachs, Bridgewater, Renaissance Technology, pension funds, sovereign wealth funds to measure your portfolio risk. Big picture, after covering syllabus till now, we have now built the entire hierarchy. How do we proceed from probability to expectation, expectation to variance, variance to standard deviation to covariance, to correlation, to portfolio variance, to Markowitz optimization, modern quantitative finance, everything from CAPM to Black-Scholes to WAR to machine learning risk model ultimately sits on top of these foundation, right? Okay. Then we get into the next part, which is risk management, measuring tail loss and fluctuation. This slide is extremely important because it explains a major weakness of variance. Until now, we have assumed risk is equal to variance and risk is equal to sigma, but in reality, tails and risk management care much more about how much can I lose in a disaster and then how much do I fluctuate on a normal day. These distinctions created on risk management, volatility risk, we have done portfolio volatility, sigma p under root of variance. This formula comes directly from Markowitz portfolio theory. What does volatility measure? Volatility measure typical fluctuation, day-to-day volatility, normal uncertainty. Think of how much does my portfolio wiggle around, not how much can I lose in a crash. Problem with variance is that suppose portfolio is 99% probability plus 1% 99% probability of +1%, 1% probability of -50%, portfolio B always 0.5%. Both have similar variances. But every investor prefer B. Why? Because variance treats upside and downside equally. Humans don't, right? Then we have your VAR, right? That's why you study VAR, right? VAR is the loss threshold exceed with probability 1 minus alpha. For example, 95% VAR of 95% means, let's say, $10 million. There's only a 5% chance that losses exceed $10 million. Visual intuition here is that imagine a loss distribution function. VAR identifies a cutoff point in the left tail. This boundary is VAR, right? And then we have expected shortfall. The problem with VAR is that it tells us whether disaster starts, not how bad it becomes, right? Conditional VAR helps us do that, right? So it tells us expected loss when loss is greater than VAR. Meaning if disaster happens, what is the average loss? Example, 95% VAR is $10 million. Worst 5% loss is 10, 15, 20, 30. Expected shortfall will be the average of 10, 15, 20, 30. Why regulators love expected shortfall? Because after 2008 crisis, regulators realized VAR ignores disaster severity. Basel III and FRTB increasingly emphasize FRTB's fundamental review trading book. Expected shortfall rather than VAR. The quant inside here is, why is expected shortfall considered a coherent risk measure while VAR is not? Answer is expected shortfall satisfies sub-additivity. VAR does not always. This is the favorite FRM question we have, right? Then we get into the next part, which is your slide number 22, where expectation and variance show up in practice. Now the course connects mathematics to real financial institution, asset pricing model. Every pricing model begins with expectation. General pricing formula, price is equal to expected value discounted payoff. This single idea powers bond pricing, option pricing, credit pricing, insurance pricing, Black-Scholes. Example we have, right? Option value is given here, right? Which we must understand option value is equal to Black-Scholes, C is equal to expected value, not expected value. The expected value is there, but you have to take the exponential of that minus ERT, expected value, and then we have to do Q is there for risk neutral measure, guys, right? So don't be surprised. What is this Q, right? And ST minus K plus is your payoff. Notice something. Everything comes back to expectation. Portfolio construction, portfolio manager allocate capital using expected return and your VAR, right? So that's what we have. Question they ask is which asset has a highest expected return, which asset has lowest risk, which combination maximize Sharpe ratio. This directly leads to maximization of expected value of R minus RF divided by sigma. Risk analytics. Every bank produces daily volatility reports. Metrics include volatility, VAR, expected shortfall, stress testing, what happens in market fall 30%. Real bank example is at Goldman Sachs, JP Morgan, Citi, HSBC. Every trade index produces daily profit and loss, daily VAR, stress losses, capital uses, all built on expectation and variances, right? Which we need to understand. Okay. So this is done. Then we get into the next part, which is key takeaways, very summary. Now, mean and risk measure, the slide summarize everything. Expectation, EX, measure central tendency, long-run average, trivial outcomes. Finance interpretation, expected return means expected return, variance. Formula is given, E, expected value of X minus EX square. Measure spread, uncertainty risk, large variance, high risk, small variance, low risk, standard deviation, sigma, under root var, variance X, measures volatility, practical risk. Why use standard deviation? Because it has the same unit as original variable. Example, return units percentage, variance unit percentage square, standard deviation unit percentage. Much easier to understand. Please understand when we have statistics for mean, we use in finance expected return, variance, we use risk, standard deviation, we use volatility, covariance, co-movement, correlation, diversification. Okay. Then we get into why these concepts matter in finance, because this is the grand conclusion of the lesson. Asset pricing determines the expectation determines the value. Bond pricing, price is equal to present value of expected cash flow. Option pricing, price is equal to expected value of discounted payoff. Trade pricing, expected loss is equal to PD into LGD into AD, probability of default into loss given default into exposure default, all expectation based. Portfolio optimization, Markowitz framework, expected return, ERP is equal to your this value formula is given, VAR is also given, this is covariance. Metrics, this creates the efficient frontier. Risk management, banks must answer how much do we expect to earn, expected return, how much can we fluctuate, sigma, how much can we lose, variance, how bad can disaster become, expected shortfall, the entire quant finance ecosystem. Notice the chain. Expectation to variance, to standard deviation, to covariance, to correlation, to portfolio variance, to efficient frontier, to CAPM, to Black-Scholes, to VAR, to Monte Carlo simulation, to modern quant finance. Please understand, if there is one sentence you should remember from this entire chapter, it is expectation measure reward and variance standard deviation measure risk. virtually every model in quantitative finance, from portfolio optimization to derivative pricing. And risk management is built on balancing these quantities. That is reward versus trade-off is the mathematical heart of finance, right? With that, we have completed the theory part, but we have to do some questions. Easy question, guys, right? So now we have your questions here. We will do quickly because I don't think there is any challenge here in the question because these are pretty, what you say, straightforward kind of questions, right? So first question is, we have been given your two asset expected return, or one is given, two is given, weights are given, right? So find, how do you find this value, right? This is weighted average, guys. 0.6 into 10 plus 0.4 into your 0.06, right? Solve it, guys. This is very simple. Expected portfolio return is the weighted average of asset return. This is school stuff, right? Guys, you can solve it your own, right? So that's what we do, right? What is happening basically? W1, right? W2, this is your expected return of the portfolio. Right? Answer is 8.4. Very simple, very straightforward, guys. Expected portfolio return is the weighted average of asset returns, right? Very simple. Next one is return distribution, right? Return distribution given. See the expected value, again, we have to find out here. Mu expected value is equal to 0.5 into 0.1, right? Plus 0.5 into minus 0.05 is 0.025. Variance, when I have to find, the question asks to compute variance. Variance, we have to find variance of R is equal to summation your PI RI minus your mu square, right? Mu square, right? So this is mu square. Okay. So now if you have to solve this, right? What is happening here? Basically 0.5 into 0.075 square, 0.5, 0.075 square, right, is equal to 0.005625. So variance measure dispersion of risk, variance measure dispersion of returns, which is risk. So you understand that, right? Very, very easy. Then we go to question number 3, right? Here again, we have been given sigma, right? So you understand sigma square P and the sigma 1 square W1 square plus W2 square sigma 2 square to W1 W2 sigma 1 sigma 2 correlation, right? You put the values 0.25 into 0.04, 0.25 into 0.0225, 2 into 0.25, 0.4, 0.2 to 0.15. You solve it, you get 0.021625, right? Correlation determines your diversification benefit, okay? Then we have your question number 4, variance of your AX, A square variance of X, right? So we are trying to find variance, right? So variance of RL is equal to C square 0.02, right, is equal to 9, 0.02, equal to 0.18, right? Leverage increases risk quadratically. Leverage increases risk quadratically, right? Remember this one. Last but not the least, right, we have another question. Stock price is given, compute expectation and variance of payoff. Again, expectation of payoff mu is equal to 0.6 into your 20 is equal to 12. Variance, when I have to find, right, variance is equal to 0.6, 20 minus 12 square, 0.40 minus 12 square. You solve this, you get 96, right? So this is the answer, right? That's it, guys. You have the solution ahead for each question. I've already solved it, but you have the solution ahead. You want to see, you can do that. With that, we have completed this chapter, guys. Not a very difficult chapter, small chapter. Understand easy things, mostly repetition, a lot of things. So I don't think this will challenge you at all. Right? Go back, revise it. You will be totally fine. And I'll see you in the next lecture. Okay. All right, guys. Thank you.